So hello everyone, today's class is going to be recorded because during the actual class the recording got corrupt. So today we're going to cover 2D arrays and sorting. So because we didn't manage to finish the 2D arrays during the previous class, we're going to talk about this today. So 2D arrays are basically just, let me show you. So during the previous class, we discussed that arrays are just basically memory in row that have name and then some size, right? And then in every single part of the array, every single element of the array is for example, in this case, integer, right? So it stores many elements in a row, and you have the ability to access it through index, right? So the indexation starts from 0, 1, 2, 3, so on to n-1, where the n is the size of the array, right? So this was the one-dimensional array. So what is the 2D array? Is array of arrays, basically. A grid you index with a row and a column. It is a very natural way to store, for example, game boards, matrix, or tables. So the way we can imagine it is basically here we declare the one-dimensional array, right? So to declare two-dimensional array, we have to put this, right? So, and the whole picture is going to be something like this, where this is the n rows, right, and m columns. And then if you access element, let's say a e g, it's going to be the element in a row e with the column g, right? So in this case, for example, 0, 1, 2, 3, 4, so 0, 1, 2, 3, and then 0, 1, 2, 3, 4, 5, 6, right? So if you want to access element, let's say e equals to 2 and then g equals to 5, it's going to be element, let's count, second the row number 2, right, which is this one, right, and then column number 5, which is this one. So basically here, right? Yes. And then we get the element over here, right? So in the same way, we can declare several multi-dimensional arrays. What it means is basically we are not kept by 2 dimensions. We can also have 3, 4, 5, and so on. As for example, n, m, x, y, and so on. And for example, we have 3, it's 3-dimensional, right? So we can imagine something like this. With basically and so on. So as we can remember from the previous class, array is static. As for example, you declare the array with some fixed size, and after that it doesn't change, right? So if we want to have something more dynamic, we can use vectors. But before we go into that, how do we traverse with let's say nested loops through the 2D array, right? So let's say just a second. So how do we traverse through array? So Usually we get, for example, the size, right, that we have as in this case like 3, 6, and then we have to input the array, right? So let's say nm, right? And then we input nm and go through the whole thing with 2 for's nested loops, where we first go through the through rows, and after we go through columns, right? So first we go through rows, which is this one, and then after we go through columns, which is m, and then we can enter for example, this is the size of the array, right? So this is the way to enter an array, right? So if you, for example, want to calculate the whole sum of the elements inside the array, we go through the whole thing with nested loops the same way and calculate the sum. As for example, we have for example sum equal to 0. We go through n rows, go through we go through m columns, right? And then each time, as we have the access to every single element, we just sum up everything into the sum, right? So sum plus equal AEG. And then we get the sum, right? Yes. So let's see how it works. Let's say we have 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. We have the whole sum. As we can see, it works. So I'm going to go through everything pretty fast without like examples and everything that much, but I hope that the whole topic is well explained in some way. So yes, another concept. For example, we have to answer not just the whole sum, but every single column or every single row, right? So let's start with first with rows. If we have to give answer for give the sum of every single row like this, how do we do that? So first we have to go through rows, right? First go through rows with 1, 4, and then for every single row we have to go through the whole column thing and then get the sum for every single row with passing every single column, right, in that row. Which means for example, let's say here we have going through the rows, and then we have some sum going through the columns, and then plussing the sum, right? And then here we have the sum of every single row, which is right? Yes. So, and in other case, if we want to, for example, get the sum of every single column, the thing that we have to do is basically just change the traversal principle. As for example, first we go through rows and then through columns. In this case, we go through columns first, fix the column, and then go down in the rows in the one fixed column, right? And for that we have to first go through the let me show you. So let's say 4, right? We have to first go through, let's call it not E, but let's call it J, so we understand better. We go through columns, and then for each column we fix some column, right? And then we go through rows. And then sum up everything over here, right? And then, as we can see, the difference is that we just fixed the column first instead of row first. This is basically just changing how it's called. Yeah, anyways, so so here we can see that 3 3 1 2 3 4 5 6 7 9 8 9, and yes, we can see that here the sum is the column sum, right? And then let's look. Yes, as I said, for arrays we fix the size first, and then after that we can't really change everything because it allocates the memory. Like we have the row of the memory, right? As like this is the general memory that we have. We just find some free space over here and then allocate to the array, and it's fixed and we can't do anything with that, right? But in case of vector is implemented in some way that you can just push and pop elements into it, right? So we are not limited with it, like. And then if you want to have sign dynamic to the array, we can have, for example, vector of vectors, right? And the way we yes, if the sizes depends on input, we use 2D vector, and we build the vector with rows and columns like this. Here we can see we have vector of vector, and then which is called G, and we have rows, right, which is basically n here. And then we have another, basically, if you remember from the class, the way you set a vector as, like, we put, for example, the amount of elements and then the actual element, right? This is like the for one-dimensional vector, but in this case, for every single index of the one vector, there is another vector. So here we have n vectors, which represent the n rows, and then we have in every single vector, in index, we have another vector, which represents the whole row. Does it make sense? So here we can see for the vector we first have the amount of rows and then amount of columns, right? So n and m, for every single n here we have the m columns, which represent the whole row, right? Okay, let's see what else we have. So we are going to finish on the multi-dimensional arrays on this. During the actual class we covered many examples, which right now I'm not going to cover, sadly, but yeah. Let's talk about sorting. So sorting, why we use sorting, what is sorting? So sorting is arranging the elements in some order. By default it's like ascending, right? So for example, we have some array which is like let's call it of size equal to 5, 4, 3, 2, 5, 1, right? And then after sorting it becomes 1, 2, 3, 4, 5, right? So we just sorted everything in ascending order, right? How it can be like how can we benefit from it? So it matters because a sorted array unlocks fast follow-up steps, binary search, plotting duplicates, finding the smallest or largest few, and many greedy strategies. It's very useful. And then by practice we don't really write sorting like on our own. We just call the already implemented like function, which is called sort, std sort, right? So which runs in n log n, the fastest complexity for sorting, and it's in the library algorithm, right? We have to also include algorithm. So how do we like write the syntax for sorting? Let's say we have a vector and then we have to sort the vector, right? So let's say we have n elements, right? We have n elements, then basically we input those n elements, and then we store it in a vector v. And then how are we going to sort it, right? So first we have the input. Let's say we also have to check the output if it's like actually sorted or no, and then for that we're going to write the output looking like this. And then the actual sorting part. So here the the syntax for it is the function sort brackets, and then in sort we first argument is the beginning of the thing that we're sorting, and then the end plus 1. So in case of not end plus 1, end. So in case of vector, basically it's going to be the beginning of the vector, v dot begin, and then the end. So if you write, for example, 5, 4, 2, 3, 1, 5, 1, let's say, we get the sorted vector, right? As here we can see. Let's copy this example that we can use later on. So yeah, and then how does the logic work? Like yn, because we here, for example, if it was like an array, let's say array a, and then we have like I equal to x, right? So if we want to also sort the array, we have to write not begin or end, because it's array, the syntax is different. We write sort a plus n. How does that work? So as we can remember, array is just some allocated like row of memory connected to each other. Like it's just a chunk of memory in a whole memory thing, and we call a, and the a also represents the beginning, the location. So we put, and it's like the first element. So we put a, right, and then we put a plus n, which is just basically n, let's say, like indexes to the right, and then if we have n elements in general, it's going to be the last element plus 1. And this is the syntax, right? So in this case, if we have the vector, it's going to be last element plus 1, which is the vn, right? So this is how you put how we write the sort function. Let's see. Let's also talk about how the classic sorting works, right? So because we can use the sort function from the algorithm library, but it's also very important to understand how does the sorting by itself works. So in case of the sorting algorithms that we are going to cover today, they are going to be slow and square because the actual n log n algorithm, which is either merge sort or quicksort is used in the function, they are very fast, but they are also more complex, right? But here, 3 examples that we are going to cover are selection sort, bubble sort, and insertion sort, and they are simpler. Yeah, sorry for that. Let's continue. So basically today's lecture is also going to cover 3 examples of 3 simple sorting algorithms that are working not n log n but n square, right? So first is going to be the selection sort. Selection sort repeatedly finds the smallest remaining element and puts it in a place. So let's have an example how it works, right? So here we can see, let's see. Yeah, so let's say we start from, let's have an example of array, which is 4, 3, 2, 1 here, and then 5 here. And then the selection sort is going to look for the smallest element in the array and then put the element at the beginning. As for example, in this case, we find 1, right, as the smallest, and we put 1 into the into the first place. We swap it with the first element. So here 1 comes here and 4 comes here, right? And after that, we already know that the first element is already sorted. It's in the right place. So we look for the smallest element in the rest of the array, which is this part. So in this part, we look for the smallest element, which is 2, right? So after finding the smallest element index, we again swap it, but this time not with the first element, with the second element, because we know that the first element is already sorted, right? So we put the 2 into here and then 5 into here, and then after that we note that the first 2 elements are already sorted, right? So okay, let's change the array a bit. Yes, let's say we know that the first 2 elements are already sorted, so we look for the smallest element again, but for the rest of the array. We find the element here, and then we again swap it, but this time with the third element, because we already know the 2 elements here are already sorted. And in this way, by swapping and by locating the smallest element and swapping it with the first not sorted element, we can build the whole array sorted. The way it works, let's write the code, right? So here we have the array. No, we have the vector. And then we start and we go how many times? We go n-1 time, because we know that after we do the whole thing n-1 times, we are going to have first n-1 elements already sorted, right? Because every single time we put one element into right space, one element into right space, and so on, n-1 time, and then after n-1 times, the last element is already going to be in a right space by default, like it's inevitable. So 1, 2, 3, and then the biggest one is left there, right? So n-1 times, and then each time we go through the array, right? And then we go from until n, and we start from e. Here e is the amount of elements already sorted. So in this case, from the very beginning, none of the elements are sorted. So we start searching for the smallest element from the very beginning, from the 0. And after we put the first element from somewhere here, like the smallest element here, it turns into 1, right? And then we know that one element is already sorted, so we start from here. So we keep an index. And an index is going to store the smallest element's index. As for example, and then we are going to update it every single time. So if the v-int is bigger than vg, right? So this means that vg is smaller than v-int. So we update the int this time, right? And by the end of this for, the index is going to store the smallest element. So after that, we are going to swap the smallest element that we located, which is the int, with the e, right? Because we are going to have like a sorted and not sorted. And every single time we're going to locate the smallest element here, and put it over here. So +1 to this and -1 to this, right? And then this part, the index of it is e. So we swap it with the e. And then let's see how it works, if it works. Yes, it works. So this was the selection sort. There is another type of sort which is called bubble sort. It repeatedly swaps adjacent out of order pairs, and the largest value bubbles to the end each pass. So how do we understand it? Let's say back to the same, different example, as 8, 7, 3, 2, 1, 5, 10, and let's say 4. So bubble sort works in a way of every single time we pass through the whole array, let's say a whole array, and then every single time, as we see, we compare two elements adjacent to each other, like neighbors. We compare. If we want to sort the whole array like increasing order, if we see something decreasing, as for example, if we see this one, this is wrong, right? Or let's say not this one but this one, the first pair. So it's not increasing, it's decreasing, so it's not right, right? So what do is we change the place of this. We swap the neighbors 7, 8, and then we continue going, and then for example we see this, and then we swap the elements, right? 1, 8, and then again, and so on, right? Here it's again swapping because and then again, and then here in this case it's correct, we don't touch it because it's increasing order, right? We move forward. Now we compare this with this, right? And then we see that we should swap it, right? So yes, and then we, after we finish this thing, we can see that the biggest element, which is 10, bubbled as it was saying to the top part, to its place, right? Because we kind of carry the biggest element with us, right? If we see biggest element, it just carries with us because we swap it with this, and then we compare this with the neighbor, and then again swap it, and then compare with the neighbor, swap it with compare neighbor, and then so on, so we get the highest element over here in its place. And after that we go through the whole array again, doing the same exact thing, and in this case we get the highest element of the rest bubbled into the second highest place, right? So by doing it again, we're going to have the whole array sorted. The way we implement it is, so we do this n-1 times, right? Because by the end, as we could see in the selection sort, this time it's a bit different, right? So we get elements over there to the highest place. Again, we sort the array from the back, and then we get the last element, the n time, already sorted, so no need. So n-1 times, right? And then every single time we go through the array from 0 to n minus e. Why n minus e, right? So because during the eth time we are going to have already e elements sorted at the end. As for example here, e is equal to 1, we have one element sorted. After the whole array, it's going to look like something like 1, 7, it's lagging, sorry, 3, 7, 2, 7, 5, 7, then nothing here because it's correct, and then 4, 8, right? So as we can see, and then e changes equal to 2, right? And then here we have already 2 sorted elements, right? So this next time we're going to look only this part, and these elements that are less than n minus e, we get rid of those elements. We don't consider them because there is no need, because they're already correct. And then every single time, and then also we have to look not for this, because like the way that we do is we compare with the next neighbor, right? E with E plus 1, right? So if we want to do this with this, it's correct. But then this one, there is no neighbor to compare with. From here, we don't consider them. So we are also doing, let's see, we are also doing -1. And then we see if VG, let's say more than VG plus 1, we swap VG with VG plus 1. And here it's going to work, right? Yes. As we can see, it works. And again, the time complexity is O n squared, because we do something repeatedly n times, as we can see here, here, and every single time we do another for nested loop, again, which has n operations inside, so that's why it's n squared. And then the insertion sort is we grow a sorted prefix of elements, and every single time we insert a new element into the correct spot. For example, we have let's say numbers. Let's copy the numbers from here. Oh no. 8, 7, 1, 10, 5, 4, 6. The insertion sort works. Let's say we are like in the middle of the insertion sort. We assume this is sorted as, for example, 1. Let's say it's sorted already. Doesn't matter. 7, 8, 10. And then we have this part 5, 4, 6. The way we can, for example, sort it, right, is, for example, add 5. This is already sorted, right? We add 5 into the right space over here. So it becomes 1, 5, 7, 8, 10, 4, 6. And then we consider the next one. We add 4 into the right space, which is over here, right? So it becomes 1, 4, 5, 7, 8, 10, 6. And then we consider this one. We put it in the right space, which is over here. And then 1, 4, 5, 7, 6, 7, 8, and 10, right? So basically, the way insertion sort works, we every single turn we get one element, the new element, and insert it into the sorted prefix, the right spot, as I showed here. And then if the array doesn't have any, let's say, this kind of sorted prefix, how do we understand it? Basically here, 8, 1, 7, 10, 5, 4, 6, right? So 8 is already kind of sorted, right? By itself, 8 is sorted array, just 8. And then the new element is 1. We add 1 to the already sorted prefix. The correct spot is this. And then we add this. The correct spot is this. Sorry. So my pen died, so I'll just continue writing with the finger. So as we saw, the insertion sort works this way, and here, for example, when we don't really have like a base, like prefix, we just have the 8 as like sorted by itself, and after that we start to add more and more and more, like on top. from like 1 here to here, and then we have already this much sorted, and then 7 goes here in between, and then 10, and and then basically grow the like sorted prefix from very 0. That's why it works. And then let's try to also write the code for that. So let's see. So we start from second element, not actually the first, because the first is already sorted, right? We assume that, like, not assume, like, we just know that the first element is already sorted, and then after that, as we have the element that we have to, like, the new element, which is E, we have to, let's say, go back, look where is it, like, where does it belong, and then put the element over there, right? So the way we do that is, let's have another thing called G, and then while G is more equal than 0 and Vg minus 1 is more than Ve, right? Or let's say we have a key. There are many ways to write this, so let's try this way, where we store the element here in key, and then we compare with key, and then we look if the Vg is more than key. Basically that means, for example, here we are trying to put this element over this part, and then if the element over here is greater than the element over here, we want to do it like in increasing order, right? So we have to change this, like it doesn't belong here, it belongs somewhere over here, so this is like this, right? So if it's greater than key, we have to move it, right? So instead, the way we do it is basically like we have the elements, right? This is our new element, and we have to put it over here, let's say, somewhere. So the way we move it is basically, for example, if we have to move this here, and every single element is going to go here, 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 right? And then the way we do this is basically we assign this part, let's call it like 0, 1, 2, 3, 4, right? We assign 4, 3, like we move it, right? We overwrite it, and then this one, and then this one, and then this one, and then as we have here, we have like double 3, 3, right? Or like double element x, x. We assign key that we stored to the right place over here. Basically, g minus minus, basically until this continues, we just keep going, right? And then also assign the g let's see. So let's say J is the maybe the correct place that we have to put the element, no, or let's say the element that is not greater than our that is not greater than key. and then sorry. So here we see k is equal this, j is equal this, and then we check if the j is more than equal than 0, and then also and j is like greater than key. Basically we just keep going until we find the place, we find an index that is lower than key, or we just come to the -1 index. And during the whole way we assign g plus 1 like ag, basically just move the element as we said, rewrite over the next element, and then by the end we assign ag plus 1 key, right? As here for example, like 3 2 no, 3 4 5 1, right? So we keep key like equal to 1, 5 4 3, right? We also move here, like g becomes -1, and then after that +1 we change this one to 1. I hope this is more or less clear. And then we can also, for example, do sorting in custom order. Let's cover it briefly. So for example, like by default it sorts in increasing order. If you want to have like in decreasing order or something like that, we have to write our comparator for that. We give the sort a third argument, which just determines the way that sort function works for us, right? So that returns true when its first argument should come before its second. A lambda is the easy way to write the one. This is the shortest way. So let me show you a bit longer way. As for example, let's say we have the v, and then we have to let's say sort it out like this. But then we want it to be not increasing but then decreasing, right? So for that we can write a comparator which looks like this. We have, let's say we put the third argument, which is our way. This is the name of the comparator, and then we write the comparator like this. It's going to be boolean because it's either true or false, and then our way, and then here we are going to get two elements that the same type of the, for example, vector that we are sorting. So it's going to be int the const and this thing over here, which is called reference, are for the speed, because here the comparator doesn't necessarily change anything. It just compares. So it doesn't change, so that's why it's const. And then reference, I explained it in advanced division. Basically here we just passed the location, we don't have any copies and everything, doesn't matter. So just remember this is the way to write it. And then here, for example, we return true if it's the right way. Basically, if the first argument should come before its second. As for example, we return true if a equal like this. So in cases of A being greater than B, it's correct. A should come before the B. And then as we put it here, our sorting is going to be, sorry, um, our sorting is going to become decreasing order, as we can see. And in the same way, we can do several things, as for example, pairs, like write the same thing for pairs, compare the second element of the pairs instead of the default first element, and so on. We can also do it with struct. I'm not going to go deep into this right now, because I did during the class and the recording got corrupt, so sadly. And this is the short way to write the comparator, the lambda. We put this, the elements, and then the comparing. It's inline function, it's only one line. Instead of writing the whole function over there, we can just do that. We can just do that. And for example, just an example of like sorting in a problem setting. Let's say it asks like count how many distinct values we have. So we have an array, we have to count how many distinct numbers we have. Let's say we have like 1, 2, 1, 2, 1, 3, 4, 3, right? So we have 4 distinct numbers, but how do we understand that? Like, how do we know? So the way to do that is, for example, to sort everything 1, 1, 1, 2, 2, 3, 3, 4, right? And then just go through the whole thing and get the amount of different neighbors. This one, this one, this one, and then plus 1, because like it's like pair, like this, but also plus 1 from this side, right? So 4 distinct numbers. Sorting can have very different usage, and it's very useful to know. So this is it for the class. Sorry for the, let's say, lost actual class recording. Hopefully it won't repeat afterwards. And yeah, thank you for the class. I'm going to share this PDF in the description, and so you can take a more detailed look. Also some links to read from for better detailed information, and also the practice problems that you can practice on. And also I'll be sharing the Excel thing where we have the problem set that you can practice, like different topics. So you just put your name over there and then just mark everything which is complete. So yes, thank you for the class, and see you during the next class. Thank you.